In the deserts of Arizona and California, under a relentless sun, lie the silent giants of aviation. Thousands of commercial airliners, parked in perfect rows, their engines covered, their windows gleaming like vacant eyes. This is the aircraft boneyard. From the ground, it looks like a final resting place, a testament to engineering marvels, now rendered obsolete. But this image, this idea of a graveyard, it is a carefully constructed myth. The industry will tell you a startling statistic that up to 90% of a modern aircraft, by weight and beak, can be recycled or reused. 90%? That number feels, well, it feels impossible when you look at these complex machines. These flying cocktails of exotic metals, composites, and electronics. It seems like a marketing line, right? A piece of corporate greenwashing to make us feel better about the carbon footprint of flight. But what if it's not? What if this dusty expanse isn't an ending, but a beginning? The truth is, these boneyards are not graveyards. They are high-tech disassembly plants, operating on a scale that is difficult to comprehend. They are the beating heart of a hidden, multi-billion-dollar circular economy. The real story isn't about whether we can recycle a plane.
Here in the Boneyard laboratory,
is how we do it.
Decommissioned airframes aren't stripped
what
for parts.
That process
they
reveals
undergo a planned
about
metamorphosis.
The future of manufacturing, and whether that impressive 90% figure is hiding a much more complicated and challenging truth. To understand the 90% claim, you have to stop thinking of this as a retired Boeing 747 and start seeing it for what it truly is: a 200-ton flying inventory of high-value, certified components. The process is called parting out, and it's less like scrapping a car and more like performing a meticulous organ transplant. The first and most valuable organs are the engines. A single-use jet engine can be worth millions of dollars. Inside are turbine blades, forged from single crystal superalloys. Materials designed to spin at 10,000 RPM, while withstanding temperatures hotter than molten lava. These aren't melted down. They're carefully removed, inspected, recertified, and sold back into the aviation ecosystem to keep other planes flying. This is the peak of reuse, and it accounts for a massive portion of a decommissioned aircraft's value. Next comes the nervous system, the avionics. The flight decks and electronics bays are a treasure trove, not just of functional computers and displays, but of raw materials. We're talking gold, silver, palladium in the circuit boards, and a host of rare earth elements like neodymium and terbium in the powerful magnets of actuators and sensors. In a slightly conspiratorial, secret knowledge tone, extracting these isn't simple smelting. It's a form of urban mining, requiring complex chemical and electrical processes to reclaim elements that are geopolitically sensitive and environmentally costly to mine from the earth. In a faster listing tone, even the seemingly mundane parts are part of this calculus. The landing gear, with its specialized high-strength steel alloys, is almost always refurbished. The auxiliary power unit, the small jet engine in the tail, is another high-value component. The aluminum skin of the fuselage, well, that's the most straightforward part. It's high-grade aluminum easily melted and recycled into everything, from new aircraft parts to beverage cans. This is the brute force recycling we all imagine, but it's only one piece of a much larger, more sophisticated puzzle. Now, multiply that intricate process by hundreds of aircraft every year across multiple facilities globally. The sheer scale is staggering. The largest Boneyard, Davis Monthan Air Force Base, is a military facility. But civilians, like the Mojave Air and Space Park, or the Pinal Air Park in Arizona, manage vast fleets of commercial planes. These aren't chaotic junkyards. They are meticulously organized logistical hubs. And managing this industrial ballet requires a digital revolution. When an aircraft is selected for teardown, its entire maintenance history, every part, every serial number, every flight hour, is logged into a global database. Companies use AI-driven inventory systems to track millions of components. Think about this. A technician can scan a barcode on a hydraulic actuator in the Arizona desert, and an airline maintenance manager in Singapore can instantly see its service life, certification status, and purchase it for overnight shipping. This digital nervous system turns a field of retired planes into a global, on-demand, spare parts warehouse. The disassembly itself is a blend of skilled human labor and emerging technology. You have highly trained airframe and power plant mechanics, the same people who keep planes flying, now working in reverse. They know precisely how to disconnect a wiring harness without damage or remove a control surface. They are increasingly aided by advanced robotics. No, we're not talking about humanoid robots, but specialized, high-precision plasma cutters, guided by laser scanners that can carve up a fuselage along precise lines, separating different aluminum atoms to prevent contamination and maximize recycling value. Even the interiors present a unique challenge at this scale. Inside a single plane, you have thousands of pounds of plastics, a child armored carpets, and fabrics, all treated with fire retardant. For decades, this material went straight to landfill. But now, specialized firms are developing processes to shred these materials, chemically separate the fire retardant compounds, and reprocess the base polymers and fibers into new products, from automotive insulation to flooring. This is the last mile of recycling. The difficult, less profitable work required to push that recovery rate from 80% towards that magic 90% number. It's a highly efficient system. It's been perfected. But it was perfected for aircraft made primarily of aluminum. But the fleet is changing. The Boeing 787 Dreamliner and the Airbus A350, well, they're not metal birds. They are black airplanes with over 50% of their structure made from carbon, fiber, reinforced, plastics, or CFRPs. And this is where the entire happy recycling narrative hits a wall, a hard wall. The industry has set an ambitious target: zero waste aircraft recycling by 2040. That would work. On the surface, it's a noble goal. But when you look at composites, it seems almost fantastical. You see, unlike aluminum, which can be melted and reformed endlessly, most aerospace composites are thermosets. Think of it like baking a cake. You can't unbake the flour, eggs, and sugar. The chemical bonds are permanent. You can't just melt a 787 wing and mold it into something new. So what can you do? The current most common method is to chop it
As the temperature rises,
and
the
use it as
aluminum
filler
lattice
in
melts and
concrete or
reforms.
low-grade plastics.
The
vehicle
thermoset
stage.
polymer,
That's
however,
technically
irreversibly
recycling.
chars and
But let's
burns.
be
We can reverse the
honest.
footage, but the chemical
It's
reaction
really
of baking cannot be
downcycling.
undone.
It
The
destroys
cake remains
the entire
baked.
value of the meticulously engineered carbon fibers. More advanced methods exist, like pyrolysis, which uses high heat to burn off the plastic resin and recover the carbon fibers. But the process is energy intensive, and the recovered fibers are shorter and weaker than the virgin material, limiting their use in new aircraft. This creates a brutal economic equation right now. It is almost always cheaper and more effective to produce new virgin carbon fiber than it is to recover and recertify recycled fibers for aerospace applications. And until that economic reality flips, the zero reader waste goal for composite aircraft remains an aspiration, not a plan. The technical hurdles are significant, but the economic barriers are the real gatekeepers. You can to a truly circular economy for the next generation of aircraft. This highly efficient system, it's been perfected, but it was perfected for one thing: aircraft made primarily of aluminum. But the fleet is changing. The Boeing 787 Dreamliner and the Airbus A350, well, they are not metal birds. They are black airplanes with over 50% of their structure made from carbon fiber reinforced plastics, or CFRPs. And this is where the entire happy recycling narrative hits a wall, a hard wall. The industry has set an ambitious target: zero waste aircraft recycling by 2040. On the surface, it's a noble goal. But when you look at composites, it seems almost fantastical. You see, unlike aluminum, which can be melted and reformed endlessly, most aerospace composites are thermosets.
We can't
Think
cut
of
this
it
like the others.
baking a cake.
It's mostly carbon fiber.
You can't
These saws won't
unbake
do anything.
the flour,
We need specialized equipment.
eggs,
This changes
and
everything.
sugar. The chemical bonds are permanent. You can't just melt a 787 wing and mold it into something new. So what can you do? The current most common method is to chop it up and use it as filler in concrete or low-grade plastics. That's technically recycling, but let's be honest, it's really downcycling. It destroys the entire value of the meticulously engineered carbon fibers. More advanced methods exist, like pyrolysis, which uses high heat burn off the plastic resin and recover the carbon fibers. But the process is energy intensive, and the recovered fibers are shorter and weaker than the virgin material, limiting their use in new aircraft. This creates a brutal economic equation. Right now, it is almost always cheaper and more effective to produce new virgin carbon fiber than it is to recover and recertify recycled fibers for aerospace applications. And until the economic reality flips, zero waste on a goal for composite aircraft remains an aspiration, not a cunning plan. The technical hurdles are significant, but the economic barriers are the real gatekeepers, and it could to a truly circular economy for the next generation of